The cybersecurity landscape has undergone a dramatic transformation as organizations worldwide struggle to secure distributed workforces, cloud-native applications, and increasingly sophisticated cyber threats. At the forefront of this evolution stands Secure Access Service Edge, or SASE, a revolutionary architecture that converges networking and security capabilities into a unified cloud-native platform. This comprehensive analysis not only examines the current state of SASE implementations and the critical role of zero trust network access in modern security frameworks, but also provides strategic considerations that will equip organizations for their digital transformation journey. The SASE market represents one of the most significant paradigm shifts in the history of enterprise security and networking, with market valuations reaching $15.52 billion in 2025 and projections indicating growth to $44.68 billion by 2030 at a compound annual growth rate of 23.6%. SASE has evolved from an emerging technology to an essential infrastructure. This explosive growth reflects the fundamental changes in how organizations operate in an increasingly digital-first world. The first quarter of 2025 alone witnessed remarkable momentum, with global SASE revenue rising 17% year over year to $2.6 billion, propelled by a 21% increase in single vendor deployments. This trend underscores enterprises' strategic shift toward consolidating their security and networking infrastructure around unified platforms that offer simplified management, tighter policy control, and reduced operational complexity. The market's maturation is evident in its consolidation patterns, with the top 6 vendors, Zscaler, Cisco, Palo Alto Networks, Broadcom, Fortinet, and Netskope, collectively capturing 72% of the market share. This concentration reflects enterprises' strategic shift towards comprehensive, integrated solutions over fragmented point products. It signals a clear shift away from best-of-breed approaches towards unified platforms that can deliver consistent security and networking capabilities across diverse environments, highlighting the need for a comprehensive solution. Zero trust. Network access has emerged as the cornerstone of contemporary cybersecurity architectures, fundamentally challenging the traditional perimeter-based security model that has long dominated enterprise networks. The principle of never trust, always verify represents more than a philosophical shift. It embodies a practical response to the reality that modern organizations operate in environments where the traditional network perimeter has dissolved. The ZTNA market itself is experiencing unprecedented growth, with Kuppingercole analysts projecting the market will reach $7.34 billion by 2025, expanding at a 17.4% compound annual growth rate. This rapid growth trajectory underscores the urgency and importance for organizations to recognize that traditional VPN solutions are fundamentally inadequate for securing access to cloud-based resources and supporting distributed workforces. The shift towards ZTNA represents a fundamental reimagining of network security, moving from network-centric to identity-centric access controls. Rather than granting broad network access based on location or device credentials, ZTNA solutions verify user identity, assess device posture, and evaluate contextual factors before granting granular access to specific applications and resources. This approach significantly reduces the attack surface while providing organizations with unprecedented visibility and control over access patterns. Zscaler's Zero Trust Exchange Cloud Native Leadership. Zscaler has established itself as the undisputed leader in the SASE market, processing over 500 billion daily transactions across more than 160 global locations through its cloud-native Zero Trust Exchange platform. The company's approach to SASE reflects a fundamental architectural philosophy, building security into the fabric of the internet rather than bolting it onto existing network infrastructure. The Zscaler platform's strength lies in its actual zero trust enforcement, connecting users directly to applications rather than networks, thereby eliminating the concept of network trust. This architectural decision provides several advantages, including reduced attack surface, improved performance through direct connectivity, and simplified security management. The platform's ability to perform full SSL inspection at scale without performance degradation addresses one of the most significant challenges facing modern security architectures. Zscaler's market position is reinforced by its customer base, which serves over 8,000 organizations, including 40% of the Fortune 500 companies, with an industry-leading 5 nines availability service level agreement. Recent enhancements include native integration with enterprise applications, such as SAP, delivering zero trust network access services directly within business-critical platforms. Palo Alto Networks has emerged as a formidable competitor in the SASE space, recognized as a leader in the 2025 Gartner Magic Quadrant for Security Service Edge for the third consecutive year. The company's Prisma SASE platform represents the industry's most comprehensive single-vendor solution, delivering advanced ZTNA 2.0 capabilities with AI-powered threat protection. Prisma SASE's differentiation lies in its deep application layer inspection capabilities and continuous trust verification mechanisms. These mechanisms continuously verify the trustworthiness of the user and the device, ensuring that access decisions are always based on the most up-to-date information. The platform leverages Palo Alto Networks' patented user ID, app ID, and device ID constructs to provide granular control over access decisions. This approach enables proper least privilege access by identifying applications at layer 7 and making access decisions based on comprehensive contextual information. The technical architecture of Prisma Access demonstrates sophisticated engineering, with ZTNA connector virtual machines automatically connecting to the closest Prisma Access location to ensure optimal latency while supporting bandwidth scaling of up to 2 gigabits per second per connector. The platform's default deny approach is a proactive security measure that requires explicit administrator approval for all access, providing organizations with honestly unprecedented control over their security posture. This means that unless a specific access request is approved, it is automatically denied, reducing the risk of unauthorized access. Netskope One, AI-driven cloud security. Netskope has established a significant presence in the SASE market through its comprehensive security service edge platform, which combines advanced zero-trust network access functionality with superior data loss prevention and cloud access security broker capabilities. The company serves approximately 1/3 of the Fortune 100 and maintains a powerful presence in data-intensive industries. The Netskope One platform's strength lies in its AI and machine learning-driven approach to cloud application categorization and threat detection. This capability enables organizations to gain really unprecedented visibility into cloud application usage while maintaining granular control over data access and movement. The platform's unified architecture combines secure web gateway, cloud access security broker, and zero trust network access capabilities through a single client and policy engine, simplifying management while enhancing security. Netskope's new Edge Security Cloud architecture provides both client-based and clientless browser access for private web applications, supporting diverse deployment scenarios, including mergers and acquisitions, integration, and DevOps access. This flexibility has made Netskope particularly attractive to organizations operating in complex multi-cloud environments. The SASE market continues to evolve, with several other significant players contributing to the ecosystem's diversity and innovation. Cato Networks offers a converged platform that integrates SD-WAN with comprehensive security capabilities through its SSE 360 security stack, providing a unified approach to networking and security with managed services options. Cloudflare One delivers a comprehensive zero trust platform from its global edge network, offering transparent pricing and strong integration capabilities built on a 250-plus city infrastructure. Fortinet's FortiSASE leverages the company's extensive cybersecurity portfolio to deliver agent-based zero trust network access, or ZTNA, capabilities with seamless integration into existing security infrastructures. Microsoft's entry into the market with Entra Private Access provides a cloud-based, no VPN ZTNA solution that leverages zero trust principles as part of Microsoft's broader security service edge offering. Assessment and planning framework. Successful SASE implementation begins with a comprehensive assessment and strategic planning that considers both current infrastructure limitations and future business requirements. Organizations must conduct thorough evaluations of existing technologies, including DNS protection and firewall appliances, to identify opportunities for integration and potential redundancies. The assessment phase should encompass several critical dimensions: current network architecture and performance characteristics, existing security controls and their effectiveness, identity management systems and integration capabilities, and an application inventory with associated access requirements. This comprehensive evaluation provides the foundation for developing a phased implementation strategy that minimizes business disruption while maximizing security benefits. Phased deployment methodology. Industry best practices strongly recommend a phased approach to SASE implementation, beginning with small-scale deployments before scaling to enterprise-wide adoption. This methodology enables organizations to optimize configurations, customize policies, and ensure that critical resources remain accessible during the transition period. The phased approach typically follows a structured progression pilot deployment with a limited user base to validate functionality and performance, canary testing across diverse use cases and user populations, gradual expansion to additional business units and locations, and full-scale deployment with comprehensive monitoring and optimization. This methodology ensures that network controls are properly fine-tuned and that the organization can adapt to any challenges that arise during implementation. The foundation of successful ZTNA implementation rests on robust, identity-driven authentication and access controls. SASE solutions are purpose-built to require authenticated access with continuous verification, representing a fundamental departure from traditional perimeter-based security models. This shift addresses the growing need for robust security in hybrid work environments by focusing on identity-based access controls rather than network-based controls. Organizations must invest in comprehensive identity and access management systems that can integrate seamlessly with SASE platforms. This includes implementing multi-factor authentication, establishing role-based access controls, and developing policies that adapt to changing user contexts and risk profiles. The identity infrastructure must be capable of supporting both human users and machine identities. As the proliferation of automated systems and IoT devices continues to expand the scope of access management. The financial case for ZTNA implementation is compelling, with studies demonstrating a 92% return on investment over 3 years, despite initial setup costs ranging from $50,000 to $250,000. Organizations can expect substantial operational savings, including a 50% reduction in security and help desk calls, 80% less effort required for infrastructure setup, and a $20 monthly savings per employee. The security benefits translate directly to cost avoidance, with ZTNA capable of reducing data breach costs by 43%, providing average savings of $1 million compared to traditional VPN approaches. Given that data breaches cost an average of $4.88 million in 2024, ZTNA represents a modern solution that significantly reduces financial risk exposure while improving operational efficiency. Beyond direct cost savings, ZTNA implementation delivers significant operational efficiency improvements, enhancing business agility and user satisfaction. Real-world examples demonstrate that organizations have experienced 300% increases in daily platform signups after implementing ZTNA, reflecting improved user confidence and system reliability. The operational benefits extend to reduced complexity in managing security infrastructure, simplified policy enforcement across diverse environments, and enhanced visibility into user behavior and access patterns. These improvements enable security teams to focus on strategic initiatives rather than routine maintenance and troubleshooting. The integration of artificial intelligence into SASE platforms represents one of the most significant trends shaping the future of network security. AI-powered capabilities are being deployed across multiple dimensions of SASE functionality, from automated threat detection and response to predictive analytics that anticipate security risks before they materialize. Organizations are leveraging AI to provide real-time insights into network behavior, automate incident response functions, and optimize security policies based on evolving threat patterns. The most advanced SASE solutions now incorporate machine learning algorithms that can identify anomalous behavior patterns, detect zero-day threats, and automatically adjust security policies to respond to emerging risks. Regulatory mandates such as GDPR and HIPAA, as well as other compliance requirements, are driving SASE adoption by prompting organizations to implement comprehensive data access, usage, and protection measures. SASE facilitates compliance initiatives by offering centralized platforms that enforce uniform security policies with built-in logging, data loss prevention, and identity-based access controls. The compliance benefits of SASE extend beyond simple policy enforcement to include comprehensive audit trails, automated reporting capabilities, and risk assessment tools that help organizations demonstrate compliance to regulators and auditors. As regulatory requirements continue to evolve, particularly in areas such as data sovereignty and cross-border data transfers, SASE platforms are adapting to provide the flexibility and control organizations need to maintain compliance. The SASE market is trending towards single-vendor solutions, with organizations increasingly preferring integrated platforms over best-of-breed approaches. This consolidation reflects enterprise demand for simplified management and reduced complexity in security operations as organizations seek to minimize the overhead associated with managing multiple vendor relationships and integration points. Several factors drive the evolution towards single-vendor SASE solutions, including the complexity of managing multiple security tools, the need for consistent policy enforcement across diverse environments, the desire to reduce the total cost of ownership, and the requirement for unified visibility and reporting capabilities. As the market matures, vendors are investing heavily in platform integration and unified management capabilities to meet the evolving demands of these customers. Despite the significant benefits of SASE implementation, organizations face substantial challenges in deploying these solutions effectively. Common deployment mistakes include insufficient planning, selecting inappropriate providers, inadequate skill development, and failing to establish ongoing monitoring and evaluation processes. The complexity of SASE deployment stems from the need to integrate multiple technologies while maintaining both business continuity and a robust security posture. Organizations must navigate the convergence of networking and security disciplines, each with its own specialized requirements, vendor relationships, and operational procedures. The successful implementation of SASE requires organizations to develop new capabilities and adapt existing processes to support converged networking and security operations. This transformation often requires significant investment in training and skill development as traditional network and security professionals must learn to work with integrated platforms that span both disciplines. Organizations can mitigate these challenges through comprehensive training programs, strategic partnerships with experienced vendors and consultants, and phased implementation approaches that allow teams to develop expertise gradually. The key is to recognize that SASE implementation is as much about organizational change as it is about technology deployment. Organizations embarking on SASE implementations must develop comprehensive vendor evaluation frameworks that consider both current capabilities and the alignment with their future roadmap. The evaluation process should encompass technical capabilities, including coverage and performance characteristics, security features and integration capabilities, management and operational tools, and support and professional services offerings. Given the strategic nature of SASE investments, organizations should prioritize vendors that demonstrate strong financial stability, continuous innovation, and alignment with enterprise requirements. The vendor selection process should include pilot testing, reference customer interviews, and a comprehensive evaluation of the vendor's ability to support the organization's long-term strategic objectives. Successful SASE implementation requires a clear roadmap that aligns technology deployment with business objectives and organizational capabilities. This roadmap should establish clear success metrics, define implementation phases and milestones, identify resource requirements and dependencies, and establish governance frameworks for ongoing management and optimization. The roadmap must also account for the evolving nature of both technology and business requirements, building flexibility to adapt to changing circumstances and emerging opportunities. Organizations that approach SASE implementation with a strategic, long-term perspective are more likely to realize the full benefits of these transformative technologies. The convergence of networking and security functions within SASE platforms represents a fundamental shift in how organizations approach cybersecurity and network management. As the market continues to mature and consolidate, enterprises that adopt these integrated solutions will be better positioned to secure their distributed workforces and hybrid cloud environments while maintaining operational efficiency and a positive user experience. The evidence is clear that SASE and ZTNA implementations deliver significant benefits across multiple dimensions. Enhanced security posture through identity-driven access controls, improved operational efficiency through simplified management, and substantial cost savings through reduced infrastructure complexity and breach prevention. However, success requires careful planning, selecting the appropriate vendor, and an ongoing commitment to security best practices. The future of SASE lies in continued innovation, particularly in the integration of artificial intelligence, enhanced automation capabilities, and deeper integration with cloud-native architectures. Organizations that adopt this transformation today will benefit from enhanced security capabilities, streamlined operations, and improved scalability to meet future business needs. The journey towards SASE adoption is not merely a technology implementation, but a strategic transformation that positions organizations for success in an increasingly digital and distributed world. As we look to the remainder of 2025 and beyond, the SASE market will continue to evolve, driven by shifting business requirements, emerging threats, and technological advancements. Organizations that invest in SASE today are not just improving their current security posture, they are building the foundation for future resilience and competitive advantage in an increasingly complex and interconnected world. The role of AI in transforming secure access service edge or SASE frameworks is really pivotal. It enhances threat detection capabilities, automates security policy enforcement, and optimizes network performance through real-time analytics and machine learning. This transformation enables organizations to respond more effectively to sophisticated cyber threats while at the same time improving the overall user experience. AI-powered threat detection represents a cornerstone capability in modern SASE frameworks, fundamentally transforming how organizations identify and respond to cybersecurity threats. Unlike traditional security approaches that rely on static rules and signatures, AI-driven systems continuously analyze network behavior to detect anomalies and potential threats in real time, automatically containing risks before they spread throughout the network. The integration of machine learning algorithms enables SASE platforms to analyze multiple dimensions of security data simultaneously, including web page source code, images, text, and URL patterns to detect potential threats with greater accuracy. This kind of multifaceted analysis significantly enhances phishing detection capabilities and protects against similar cybersecurity threats that might, evade conventional security measures. AI's contribution to threat detection within SASE frameworks includes several key capabilities. First, anomaly detection. AI continuously monitors network traffic patterns, identifying deviations from established baselines that may indicate compromise. And then, predictive threat intelligence through continuous learning and pattern recognition, AI can predict potential threats and implement preventive measures before attacks actually materialize. Behavioral analysis uses advanced algorithms to examine user and entity behavior, helping to spot suspicious activities that might hint at account compromise or even insider threats. Zero-day threat identification is another key benefit. AI can detect previously unknown threats by recognizing patterns that are similar to known malicious activities. This really helps address the critical challenge of zero-day vulnerabilities. The practical impact of these capabilities is honestly substantial. For instance, AI can identify polymorphic malware like a motet, which evades detection by changing its code structure, but still keeps its malicious intent. When suspicious activity is detected, AI-powered SASE solutions can automatically isolate potential threats, stopping lateral movement across the network while security teams investigate. AI not only enhances incident response through automation, but it also automates security policy enforcement by centralizing data from network and security events in a data lake. AI algorithms continuously learn and improve, providing actionable insights for faster decision-making. This approach in turn significantly reduces the time needed to identify and mitigate security incidents, helping to address the growing gap between the sophistication of attacks and traditional defense capabilities. The efficiency of AI in automating security policy enforcement can really relieve security teams from those tedious manual tasks, allowing them to focus on more strategic activities. As cyber threats in enterprise environments become, increasingly complex, AI-powered threat detection within SASE frameworks provides organizations with a way to manage this complexity without compromising performance or security. The technology continues to evolve toward deeper integration with zero-trust frameworks, supporting human judgment rather than replacing it, while helping people work and connect safely regardless of location. Machine learning, or ML, has truly revolutionized application discovery within SASE environments, enabling organizations to automatically identify, classify, and secure applications across their networks without relying on manual configuration. This capability addresses a critical challenge in SASE implementation, maintaining visibility and control over the expanding universe of applications that users access. So, traditional application discovery methods rely on predefined metadata or manual identification processes, which honestly can become outdated pretty quickly in today's dynamic digital landscape. On the other hand, ML-powered application discovery uses sophisticated algorithms to analyze network traffic patterns and automatically identify applications without needing any existing metadata. This approach employs techniques such as disconnected component and outlier detection, which help determine application boundaries by analyzing how virtual machines communicate with each other. The process actually works by examining network traffic flows to identify groups of systems that communicate more frequently with each other than with external systems. The ML algorithms can first automatically detect application boundaries based on communication patterns. And second, identify shared services used across multiple applications. These algorithms can determine application tiers by classifying systems with similar network behaviors. And also, they continuously update application maps as communication patterns evolve. For example, VMware's vRealize Network Insight Cloud utilizes machine learning to analyze network traffic from vSphere Distributed Switch or VMware NSX, automatically discovering application boundaries. The system can distinguish between dedicated applications and shared services, such as Active Directory or DNS, based on their communication patterns. Within each application boundary, the machine learning algorithms further classify systems into tiers, like web, application, and database, based on their network behavior and open ports. In the SASE context, this capability is particularly valuable as it enables security policies to be applied based on accurate current application mapping rather than outdated manual configurations. Palo Alto Networks has integrated a similar machine learning-based application discovery feature into its Prisma SASE offering, allowing the system to automatically identify new applications, assess their risk profiles, and adjust security policies in real time. The benefits extend beyond mere discovery. When machine learning identifies applications running on the network, it simultaneously reduces manual oversight requirements while ensuring that network and security policies remain current with the latest application landscape. This automation frees security teams to focus on higher value activities while maintaining more accurate security postures. Open Systems has implemented this approach in their unified SASE platform, where machine learning-based application discovery serves as a foundation for more intelligent security policy management. The system continuously learns from incoming traffic and historical patterns, enabling more precise application control and security policy enforcement across distributed environments. As organizations continue to adopt cloud-native architectures and SaaS applications, machine learning-powered application discovery becomes increasingly essential for maintaining visibility and control. The technology provides the foundation for other AI-powered SASE capabilities by establishing accurate application context for security policy decisions and performance optimization. So, digital twin technology is really revolutionizing how organizations test and optimize wide area network performance in software-defined access environments. By creating virtual replicas of physical network infrastructures, these digital twins allow for comprehensive testing without any disruption to production environments. They basically provide a secure sandbox where teams can evaluate performance under all sorts of conditions, before making any changes in real-world systems. At its core, a digital twin for WAN performance testing is essentially a virtual replica that stays synchronized with the physical network across time. It captures configuration, performance metrics, and even historical data. This approach lets security teams validate systems before they actually build or modify any physical infrastructure, which honestly can really improve production quality and reduce the risks that come with implementation. The testing process typically follows 4 key stages. First, there's data gathering, which involves capturing production data by attaching physical events to interfaces and synchronizing with live applications to record real-time data events. Next, we have data sequencing, where the captured events are exported and sequenced based on time and event ID, all to recreate accurate process flows. Digital replication involves creating a replica of the production environment where test applications maintain real-time synchronization with live systems. Performance testing uses this replicated environment to test network configurations, security policies, and application performance under various conditions. The benefits of SASE implementations are substantial. Digital twins allow organizations to visualize products, analyze performance, and modify virtual environments before creating physical prototypes or implementing changes to production systems. This capability is honestly particularly valuable when testing how security policies might impact application performance across distributed networks or how network optimizations might affect security posture. Real-time monitoring capabilities further enhance the effectiveness of testing. Digital twins collect data from embedded sensors in physical network components, creating a continuous feedback loop that enables ongoing optimization. This approach allows security teams to anticipate potential failures, mitigate performance issues, and verify that SASE implementations will function as expected under real-world conditions. As SASE frameworks continue to evolve with AI integration, digital twin testing becomes increasingly important for ensuring that automated security policies don't negatively impact network performance. The comprehensive testing environment allows organizations to validate that AI-driven decisions align with business requirements before deployment, significantly reducing the risk of service disruptions while maintaining robust security postures. Behavioral analytics anomaly detection serves as a cornerstone capability within SASE frameworks, fundamentally enhancing security posture by identifying deviations from standard patterns that may indicate threats. Unlike traditional security approaches that rely on known signatures, behavioral analytics focuses on detecting unusual activities that diverge from established baselines, making it particularly effective against sophisticated and previously unknown threats. At its core, behavioral anomaly detection involves identifying patterns in data that don't conform to established norms. These patterns are termed anomalies, outliers, or exceptions. Within SASE environments, this approach leverages several methodologies to identify potential security incidents. Statistical methods analyze underlying data distributions to identify outliers using techniques like Z-score analysis, which are effective for data with clearly defined distributions but may struggle with complex patterns. Cluster-based methods group similar data points and flag those that deviate significantly from these clusters, making them particularly effective for multidimensional data where relationships between variables help identify outliers. Deep learning approaches utilize artificial neural networks to process large, complex data sets with high accuracy, though they require substantial computational resources. The implementation of behavioral analytics in SASE environments focuses on several critical anomaly types that indicate potential security threats. These include users accessing applications from unusual locations or at atypical times, access from multiple locations in time frames that suggest impossible travel connections, through anonymous proxies or from suspicious IP addresses, unusual file download or upload patterns, access to suspicious domains, and atypical application usage patterns that deviate from established baselines. For effective implementation, security experts recommend adopting hybrid detection methods that combine statistical, machine learning, and rule-based approaches to enhance accuracy. Adaptive baselining is particularly crucial as it establishes baselines that continuously evolve to account for legitimate variations in behavior patterns like seasonal trends or operational changes, minimizing false positives while maintaining detection capabilities. The integration of user and entity behavior analytics, or UEBA, functionality into SASE platforms addresses limitations in traditional security monitoring tools, which often lack comprehensive behavior-based anomaly detection capabilities. This integration is particularly valuable as enterprise systems become increasingly complex with distributed applications, multi-cloud deployments, and expanded attack surfaces that honestly render traditional monitoring approaches inadequate. Unified SASE solutions offer significant advantages for behavioral analytics by delivering consistent, comprehensive data across network and security functions within a cohesive architecture. This unified approach alleviates correlation challenges that arise when attempting to analyze disparate data from multiple vendors with varying log formats, schemas, and content completeness. By implementing feedback loops where security analysts validate identified anomalies and feed results back into detection models, organizations can continuously improve accuracy and reduce noise over time. This approach enables SASE platforms to adapt to evolving threat landscapes while maintaining high detection rates for sophisticated attacks that might otherwise evade traditional security measures. Network traffic pattern recognition is a crucial component of SASE security frameworks, enabling organizations to distinguish between normal and abnormal data flows across their networks. These patterns encompass the volume, direction, and frequency of data packets exchanged between devices, providing valuable insights into network utilization and potential security threats. At its core, effective traffic pattern recognition requires, establishing baseline behaviors to distinguish between normal and abnormal activities. Standard traffic patterns typically exhibit consistency in data flow during business hours, reflecting expected internal communications between servers and endpoints, as well as regular access to frequently used applications. In contrast, abnormal patterns manifest as sudden data transfer spikes, unusual outbound connections to unknown IPs, excessive repeated requests to single endpoints, or communication with command and control servers. The analysis process employs several sophisticated techniques. Application session inspection examines application-level data over network sessions, including duration, endpoints involved, and communication patterns, providing deeper visibility than traditional deep packet inspection. Also, machine learning models analyze network traffic in real time to detect behavior deviations from established norms, identifying suspicious anomalies like data exfiltration that rule-based methods might miss. Signature-based analysis searches for known attack patterns in traffic, enabling rapid detection of established threats. However, it's less effective against zero-day exploits. Tools like TP-Prof have emerged to automate this complex process, introducing novel abstractions such as network states, which capture approximate snapshots of link utilization and traffic pattern subsequences, representing finite state automata over network state sequences. These tools help extract meaningful patterns from the overwhelming volume of network data, making the process a lot more manageable for security teams. In SASE environments, network traffic pattern recognition is particularly valuable for detecting sophisticated threats that might otherwise go unnoticed. For instance, in all-to-all communication scenarios where multiple accelerators exchange data, ideal patterns would show uniform traffic distribution. However, real-world analysis often reveals burst patterns and spikes in sending rates that could indicate potential security issues. The integration of network traffic pattern recognition with other AI capabilities in SASE platforms creates a robust security posture. NTA solutions continuously analyze network telemetry and flow records using machine learning and behavioral analytics to establish baseline normal behavior. When irregular activities occur, these systems alert security teams to potential threats, providing extended visibility regardless of whether users are on premises, in the cloud, or working remotely. This comprehensive visibility extends from headquarters to branch offices, data centers, roaming users, and IoT devices, enabling organizations to attribute malicious behavior to specific IP addresses and perform forensic analysis to track lateral movement within the network. The result is, faster threat response and mitigation, preventing business impact before significant damage occurs. Shadow IT detection has become increasingly critical in SASE environments as organizations face the growing challenge of unauthorized technology usage, especially with the emergence of shadow AI. Unlike traditional shadow IT, which involves unsanctioned hardware or software, shadow AI represents a more sophisticated threat through the unauthorized use of AI applications that often operate stealthily within browser extensions or AI-enabled SaaS tools. Most large organizations honestly vastly underestimate the number of applications in use by employees, resulting in significant blind spots in compliance and security. This problem has really intensified with the rapid adoption of generative AI tools, where employees frequently input sensitive data into personal AI tools without understanding the associated risks. So, shadow AI introduces several critical security threats that organizations really need to be aware of. First, there's improper data handling, where employees might upload proprietary or confidential information into public AI models without any IT oversight. Then you have compliance violations, which can happen when regulated data is processed through unauthorized AI channels. Prompt exposure is another big concern, since it could reveal sensitive business strategies or even intellectual property. There's also the risk of data leakage through AI tools that may store or repurpose enterprise information. And finally, there's a lack of auditability over how data is stored, used, or trained upon by third-party AI providers. Now, effective shadow IT detection in SASE frameworks relies on several advanced techniques. SaaS risk assessments really serve as the foundation for detecting shadow technologies by scanning the environment for misconfigurations, excessive permissions, and unauthorized data sharing. These assessments help identify which applications have access to sensitive data and evaluate the security posture of AI integrations. AI-specific monitoring tools provide specialized capabilities to detect unauthorized AI usage. For example, Cato Networks' KSB feature includes a shadow AI dashboard that offers user-level visibility into Gen AI tool usage across browsers, APIs, and embedded applications. This system can automatically detect and categorize both known and emerging Gen AI tools, and it does so with built-in risk scoring. Unified SASE platforms deliver comprehensive visibility by converging networking and security functions. This integration enables organizations to monitor all traffic, users, and applications from a centralized view, ensuring consistent policy enforcement across remote users, branches, and cloud environments. The unified approach alleviates correlation challenges that arise when analyzing disparate data from multiple vendors. AI-aware data loss prevention, or DLP, utilizes machine learning-based classifiers to inspect data shared with AI applications, thereby preventing the exposure of sensitive information. These systems can enforce granular security policies across all network traffic, blocking data uploads to unapproved AI tools based on user, device, or application context. 2. Effectively manage shadow technologies. Organizations should implement a multi-layered approach. First, establish clear governance policies outlining acceptable AI tools and usage guidelines. Next, promote transparency by encouraging open communication about AI usage. Then, deploy shadow IT discovery solutions to identify unauthorized applications. And finally, implement continuous monitoring to detect new shadow technologies as they emerge. By integrating these detection capabilities into their SASE frameworks, organizations can strike a balance between innovation and risk management, enabling employees to leverage beneficial AI technologies while maintaining appropriate security controls. This approach transforms a potentially chaotic AI landscape into a managed, secure ecosystem that supports rather than hinders business objectives. Stop right there. If you think SASE is just another expensive security buzzword that only tech giants can afford, you've been fed some serious lies. I'm about to destroy 5 myths that are keeping your organization stuck in the stone age of network security. And by the end of this video, you'll know exactly why everyone, from Fortune 500 companies to small businesses, are ditching their old security models for this game-changing approach. Did you know that 90% of IT decision makers completely misunderstand what SASE actually is? I've been hearing the same myths repeated over and over again, and honestly, it's costing organizations millions in security breaches and wasted resources. Today, I'm debunking the 5 biggest lies about Secure Access Service Edge that the security industry doesn't want you to know. Before we dive in, I want to take a moment to say thank you for being here. Your support fuels everything we do. If this video helps you see SASE in a new light, smash that subscribe button, hit like to spread these insights, and share this with one person who needs to hear it. Now, let's dismantle these myths together. A successful SASE implementation requires careful planning and execution. Organizations should follow a structured approach that addresses both technical and organizational considerations to ensure a smooth transition to this new security and networking paradigm. Before diving into implementation, organizations must conduct a thorough assessment of their current infrastructure and security needs. This involves identifying critical resources, applications, and data that require protection, as well as understanding how and by whom these assets are accessed. This initial evaluation helps establish a security framework that safeguards valuable assets while meeting compliance requirements. Organizations should also define clear business objectives for their SASE implementation. Whether the goal is securing SD-WAN traffic, supporting remote work, enhancing zero trust initiatives, or optimizing global connectivity, these objectives will guide subsequent implementation decisions. As Gartner recommends, engaging owners of strategic applications and workforce transformation teams during this phase ensures all requirements are properly addressed. A successful SASE deployment requires collaboration across multiple teams. Uniting security and network operations teams is particularly beneficial as it ensures both security and performance aspects are considered. Appointing a neutral project leader can help ensure all requirements are effectively communicated and met. Getting board approval is essential for network transformation projects of this scale. When presenting SASE to leadership, position it as a strategic enabler for IT responsiveness, business growth, and enhanced security. Articulate its long-term financial impact and return on investment using real-world data and analyst insights to highlight tangible benefits. With assessment complete and stakeholders engaged, organizations should develop a detailed implementation roadmap that includes budget and resource planning to ensure adequate funding and personnel, vendor selection criteria based on integration capabilities with existing infrastructure, a phased deployment approach to mitigate risks, policy development that aligns with security and compliance requirements, user training and communication plans. Many organizations find success with a segmented implementation approach. Breaking the transition into smaller, manageable units limits strain on IT departments that must simultaneously maintain legacy systems. This approach also facilitates better resource management and allows for troubleshooting issues before they affect the entire organization. Implementation should begin with a pilot phase in a controlled environment. This allows teams to test configurations, identify potential issues, and make adjustments before wider deployment. Organizations should establish clear testing protocols and dedicate resources to troubleshooting, as SASE solutions must be thoroughly tested to avoid disruptions when deployed at scale. As implementation progresses, continuous monitoring and optimization become essential. This includes troubleshooting configuration or deployment errors, testing security controls to ensure they're functioning as expected, refining policies based on real-world performance, and documenting lessons learned for future deployment phases. The complete SASE implementation typically spans 12 to 24 months, requiring patience and persistent focus on long-term objectives. By following this structured roadmap, organizations can successfully navigate the transition to SASE while minimizing disruption to business operations. Hypervisor security represents a critical but often overlooked component in the SASE architecture, particularly as organizations increasingly deploy virtualized security functions across distributed environments. As SASE combines network and security functions into a unified service delivered from the edge, the hypervisor layer becomes a potential attack vector that requires specialized protection strategies. In multi-tenant SASE environments, hypervisors manage the virtualization infrastructure that hosts security services for multiple customers. This creates an attractive target for attackers, as compromising a hypervisor could potentially expose sensitive data from numerous organizations simultaneously. When traffic flows through SASE services for security processing, it's typically unencrypted within the SASE instance itself, creating a privacy concern if the underlying system is compromised. The attack surface expands significantly as SASE providers operate across multiple public cloud providers in different countries. Various operating systems like different Linux distributions, Windows and Mac OS, and diverse virtualization technologies such as VMs, Kubernetes clusters, and containers. This diversity increases the vulnerability landscape, as attackers need only find a weakness in one component to potentially gain access to the entire system. To address these vulnerabilities, leading SASE implementations are incorporating confidential computing technologies. This approach adds a critical layer of isolation by encrypting memory content during use, preventing unauthorized access even if an attacker gains root access to the infrastructure. Confidential computing creates protected trust domains, or TDs, for SASE components. Each pod or process operates within its own encrypted memory space. The processor handles encryption and decryption as data moves between memory and processing. Memory contents remain inaccessible even to users with root privileges. This architecture is particularly valuable for protecting sensitive operations like AI-powered security functions. For instance, when Gen AI firewalls use AI models to classify content or detect jailbreak attempts, confidential computing ensures this analysis happens in a protected environment. Implementing hypervisor security in SASE requires a thoughtful architectural approach. Many SASE providers deploy their services using containerized microservices orchestrated by Kubernetes, which introduces specific security considerations at the hypervisor level. A robust SASE implementation with strong hypervisor security typically includes confidential containers that isolate each security function, attestation services that verify the integrity of the execution environment, secure service chaining that maintains protection as traffic flows between security functions, and integration with specialized security offerings through a robust hypervisor. When evaluating SASE solutions, organizations should assess whether providers offer these hypervisor-level protections, particularly for accessing critical systems like remote desktops, hypervisor-installed servers, and other sensitive infrastructure. As SASE architectures evolve, AI integration is becoming increasingly important for hypervisor security. AI-powered security functions can detect anomalous behavior that might indicate a hypervisor-level compromise, while instruction-level accelerators like Intel AMX can perform AI inferencing directly on the CPU rather than sending data to external GPUs. The cloud-native architecture of SASE represents a fundamental shift in how security controls are designed, deployed, and managed across distributed environments. Unlike traditional security approaches that rely on hardware appliances or on-premises solutions, SASE's cloud-native security controls provide consistent protection regardless of where users, data, or applications reside. SASE integrates several essential cloud-native security functions that work together to create a comprehensive security posture. Secure Web Gateway, or SWG, acts as a protective barrier between users and the internet, filtering web traffic to block malicious content and prevent access to risky websites. This cloud-delivered capability protects users from phishing attacks and malware downloads regardless of their location. Cloud Access Security Broker, or CASB, provides visibility and control over cloud applications, enforcing security policies and preventing data loss. This component is crucial for organizations leveraging multiple SaaS applications, as it maintains consistent security across diverse cloud services. Zero Trust Network Access, or ZTNA, replaces traditional VPNs by enforcing strict access controls based on user identity and context. The cloud-native implementation continuously verifies users and devices before granting access to resources, significantly reducing the risk of unauthorized access. And finally, Firewall as a Service, or FWaaS, delivers enterprise-grade security policies through the cloud, protecting remote and branch locations without requiring local hardware. This allows organizations to extend consistent security policies to all locations without managing physical appliances. A key advantage of cloud-native security controls in SASE is their ability to adapt to changing conditions. In hybrid cloud environments where workloads and data migrate between on-premises infrastructure and public cloud platforms, SASE enables dynamic security policy enforcement that follows the data. Cloud-native SASE solutions leverage and extend native cloud security controls rather than replacing them. This integration allows organizations to 1, take advantage of cloud providers' built-in security capabilities. 2, extend these capabilities with additional SASE functions. And 3, maintain consistent security across multi-cloud environments. This approach ensures that organizations can fully utilize the scalability and flexibility of cloud computing while maintaining a strong security posture across all environments. SASE's cloud-native architecture addresses the unique challenges of securing distributed users and applications by defining security, including threat protection and data loss prevention, as a core part of the connectivity model. SASE ensures all connections are inspected and secured regardless of location, application, or encryption status. The cloud-native architecture of SASE security controls provides inherent advantages in scalability and resilience. Unlike traditional security solutions that require hardware upgrades to handle increased traffic, cloud-native controls can automatically scale to accommodate changing demands. Convergence of SASE with edge computing introduces significant infrastructure and integration challenges that organizations must navigate. These challenges stem from the complex nature of modern network architectures, the incorporation of cloud-based resources, and the necessity to align in IT processes with security service edge requirements. One primary challenge is the seamless integration between on-premises infrastructure and cloud environments, which requires striking a delicate balance between security and accessibility. Organizations implementing SASE and edge computing face difficulties when traditional network security functions and WAN capabilities, historically managed by separate teams using distinct tools, must be unified under a single model. This integration demands changes to established processes, which can be particularly disruptive to organizational workflows. Limited expertise compounds these challenges, as SASE remains a relatively new concept that many organizations lack the in-house knowledge to implement effectively. This expertise gap is especially pronounced when dealing with edge computing's distributed nature, which introduces additional complexity requiring robust connectivity solutions to ensure operational fluidity. Implementing a SASE solution alongside edge computing involves, significant changes to traditional infrastructure that may have become quite entrenched within corporate working practices. This transition can compromise productivity and collaboration, while potentially creating security gaps until the new setup is fully operational. A critical challenge is fostering cooperation between networking and security professionals. Transitioning to SASE should be a joint effort that considers both network and security functions. Yet, security teams often control the deployment process, with network technicians factored in as an afterthought. This siloed approach can lead to suboptimal implementations that unfortunately fail to address the unique requirements of edge computing environments. Change management becomes essential, with organizations needing to set clear milestones and ensure stakeholders remain informed throughout the implementation process. Without careful management of this transition, organizations risk disruption to critical business operations and, potential resistance from affected teams. The quality of SASE products varies significantly across the market. Legacy security providers may lack expertise in cloud-native technologies, while other solutions may be overly complex or poorly supported, resulting in configuration issues that compromise performance. Some SASE vendors excel at network performance but provide inadequate security threat monitoring capabilities. Interoperability presents another significant challenge, as SASE combines multiple functions that may cause integration issues when deployed across edge computing environments. Few vendors currently provide truly comprehensive SASE offerings, requiring organizations to critically evaluate potential partners to ensure they deliver reliable and effective components that work seamlessly with edge computing infrastructure. As edge computing environments grow, managing and scaling these networks efficiently becomes increasingly difficult. The distributed nature of edge computing introduces challenges in optimizing data flow across hybrid environments while maintaining stringent security protocols. Organizations must carefully consider the costs associated with upgrading or transitioning to these new models, factoring in hardware, software, and training expenses. Scalability is particularly crucial in edge computing environments, where the ability to flexibly expand or contract services based on demand is essential in today's dynamic business landscape. The rapid expansion of edge computing necessitates security solutions that can scale alongside network growth, a requirement that traditional safety measures, often designed for more centralized systems, struggle to meet. Edge computing introduces data sovereignty challenges, where data must be processed and stored according to the legal and regulatory requirements of the region in which it is collected. This creates complications in managing data across different jurisdictions, requiring careful planning and compliance with various standards. SASE implementations may face challenges in meeting specific regulatory compliance standards, particularly related to data localization requirements. Organizations must ensure their SASE and edge computing deployments adhere to these regulations, which can vary significantly across different regions and industries. By understanding and addressing these compatibility challenges, organizations can more effectively implement SASE and edge computing environments, creating secure, efficient, and compliant infrastructures that support modern distributed workforces and applications. One of the most significant challenges organizations face when implementing SASE is integration with existing infrastructure and systems. Nearly half of technical executives and IT security practitioners worldwide identified this as their primary obstacle in 2024. Legacy systems, which many enterprises have invested in heavily over decades, often lack native compatibility with cloud-based SASE components, creating complex integration scenarios. This integration challenge manifests in several ways. Existing security appliances may not easily connect to cloud-based security services. On-premises applications might require special configurations to work with SASE's zero trust model. Custom-built systems may lack APIs necessary for seamless integration. Organizations attempting DIY solutions by cobbling together disjointed sets of single-purpose appliances or services typically end up with undesirable outcomes, including complex infrastructure, high latency, and unpredictable attack surfaces. Over 40% of organizations report that complexity in policy management across environments represents a major SASE implementation challenge. This complexity stems from the need to maintain consistent security policies across diverse environments, from branch offices to remote workers and cloud resources. SASE requires organizations to translate existing network and security policies into a cloud-native framework, ensure consistent policy enforcement regardless of user location or device, and maintain compliance with regulations that may vary by region or industry. As one network security architect at a Fortune 500 cybersecurity company explained, Things have changed drastically since we implemented SASE. Users are proxied through these SASE POPs, and that makes troubleshooting a little different. It's hard because we're no longer looking at things from the laptop to the application. It's really about looking things from the SASE node to wherever your user is going. A fundamental challenge in SASE implementation is balancing robust security with network performance. As organizations layer in more security controls, they often experience performance degradation that impacts user experience and productivity. This creates a difficult trade-off between comprehensive protection and operational efficiency. Deloris 2024 white paper highlights this issue as a primary challenge. Overemphasis on security at the expense of networking. We all agree that security is critical. It is non-negotiable. However, performance is as well, and many companies find it hard to balance both. A successful SASE solution requires a high-performance SD-WAN foundation before layering in security functions. Without this foundation, organizations risk creating bottlenecks that undermine the benefits of their SASE implementation. Organizations implementing SASE often struggle with visibility into their network traffic and performance. According to Enterprise Management Associates, EMA, research, monitoring the health and performance of SASE points of presence, or POPs, ranks as the second biggest management challenge. The relatively new nature of SASE creates a significant skills gap within many organizations. Most IT professionals have years of experience managing on-premises operations, but lack expertise in hybrid cloud environments. This skill shortage can slow implementation and create security vulnerabilities if configurations are improperly implemented. Organizations must conduct thorough skill assessments of their existing network and security teams to determine if they can effectively implement and manage SASE. Many find it necessary to conduct training sessions and workshops to build internal expertise. Consider engaging managed service providers or MSPs with specialized SASE knowledge. Create cross-functional teams that combine networking and security expertise. Without addressing these skills gaps, organizations risk incomplete implementations that fail to deliver the full benefits of SASE. Despite these challenges, SASE adoption continues to accelerate. Gartner predicted that by 2024, at least 40% of enterprises would have targeted strategies to adopt SASE, a dramatic increase from just 1% in 2018. This growth reflects the compelling value proposition SASE offers for securing today's distributed workforces and applications. As SASE evolves, several trends are emerging that will shape its future development. Increased convergence with edge computing to improve performance and reduce latency. Greater adoption of zero trust architecture or ZTNA principles within SASE frameworks. Expansion of multi-cloud and hybrid deployment models to provide greater flexibility. Organizations that successfully navigate the implementation challenges of SASE will be well positioned to create secure, efficient network architectures that support modern work patterns while maintaining robust protection against evolving threats. Zscaler operates as a comprehensive cloud-based cybersecurity platform that routes internet traffic through its distributed global network of data centers. It employs a four-step process to verify identity, identify connection destinations, assess risk using AI, and enforce security policies in real time. This comprehensive approach, which includes a zero-trust architecture, cloud-native design, and the ability to secure users and applications without traditional hardware-based security appliances, ensures that all aspects of your organization's security are covered. Thank you for tuning into your SASE Gateway YouTube channel. Subscribe if you want more straightforward content like this about SASE and cybersecurity topics. The Zero Trust Exchange, or ZTT, architecture is a game changer, representing a shift from traditional perimeter-based security to a cloud-native platform built on zero trust principles. Unlike conventional network security, which assumes everything inside the perimeter is trustworthy, ZTE operates on the principle of least privileged access, establishing trust based on 4 contextual elements: user identity, device, application, and content. This approach significantly enhances security by eliminating the need for blind trust. At its core, the ZTE functions as a security switchboard in the cloud, creating secure direct connections between entities and applications without exposing them to the internet. This architecture follows a systematic approach. First, identity verification, where the platform authenticates the identity of users, devices, or workloads through integrations with third-party identity providers. Next, destination determination, as the system identifies and validates the requested destination, whether it's a web page, a SaaS application, or a private resource. Third, risk assessment, utilizing AI-powered analytics, where the platform assesses risk based on multiple contextual factors, including user behavior, device posture, and content, processing over 500 trillion signals every single day. Finally, policy enforcement, where based on the gathered intelligence, ZTE enforces security policies in real time for each connection request, determining whether to grant access, block, isolate, or take other appropriate actions. The architecture's proxy-based design enables full TLS and SSL inspection at scale, allowing for comprehensive threat prevention and data protection. By terminating each connection and inspecting all traffic, including encrypted content, ZTE can block threats in real time before they reach their targets. A key architectural advantage is how ZTE eliminates the attack surface. Applications remain invisible to the internet, with the platform brokering one-to-one connections between authorized entities and specific applications, rather than directly to the network itself. This approach prevents lateral movement of threats, which is a critical factor in containing breaches and stopping the propagation of ransomware. For branch offices in remote locations, ZTE offers flexible deployment options. Organizations can either leverage existing customer premises equipment with GRE or IPsec tunnels, or deploy Zscaler connectors that establish outbound connections to the cloud, eliminating the need for vulnerable VPN infrastructure that requires constant patching. The architecture's scalability comes from its cloud-native foundation, powered by a globally distributed security cloud that processes over 200 billion daily transactions. This distributed approach ensures that users always connect to the nearest point of presence, minimizing latency while maintaining security. Recent enhancements to the ZTE architecture have expanded its capabilities to provide end-to-end segmentation between and within branches, while strengthening security across multi-cloud environments, making the platform increasingly versatile for today's complex IT ecosystems. Cloud-native security represents a fundamental shift from traditional security approaches, focusing on protecting applications built and deployed specifically for cloud environments. Unlike conventional security models that rely primarily on network-based protections, cloud-native security emphasizes an application-focused approach that integrates security throughout the entire software lifecycle, from development to deployment to runtime. The cornerstone of cloud-native security is the 4Cs framework, which provides a defense in depth approach through 4 distinct but interconnected layers. The first is the cloud layer, which serves as the foundation of the security model and includes the underlying cloud infrastructure. Security at this level involves implementing shared responsibility models, proper identity and access management, and robust security controls from cloud providers. Common vulnerabilities here often stem from identity and access management misconfigurations, like improperly set permission and overly permissive roles. The second is the cluster layer, which focuses on the Kubernetes infrastructure that orchestrates containers, key Security concerns include misconfigured network policies, inadequate access control, and insecure communication channels. Protection strategies involve enforcing secure policies, implementing the principle of least privilege, and using encrypted communication protocols to ensure data integrity. Next is the container layer, where containers package applications and dependencies, but can harbor security risks if not adequately secured. Security measures here include container scanning, minimal permissions, trusted image registries, and using the leanest possible images to minimize potential vulnerabilities. Finally, the code layer addresses the application source code with security concerns like insecure coding practices, unpatched library vulnerabilities, and inadequate access control mechanisms. Mitigation strategies involve static code analysis, vulnerability scanning, and implementing secure coding practices. Each layer builds upon the next, creating multiple defensive barriers. When one layer is compromised or misconfigured, the security of components built on top cannot be guaranteed. This hierarchical approach means that securing the base layers, cloud, cluster, and container, benefits the code layer, but not the other way around. Beyond the 4Cs framework, cloud-native security encompasses several key components. First, identity and access management, or IAM, regulates access to cloud resources according to the principle of least privilege, providing granular control over who can access specific resources and when. Next, there's network security, which involves properly configuring firewalls, ensuring appropriate traffic routing, defining strict ingress and egress rules, and implementing zero trust policies. Data protection is another crucial aspect, focusing on encrypting data both at rest and in transit, so attackers can extract value even if data is compromised. And finally, cloud security posture management, or CSPM, continuously monitors cloud environments to detect and remediate misconfigurations and compliance violations, while offering visibility across multi-cloud environments. The cloud-native security model is not a static state, but a continuous journey of improvement that involves gaining visibility into the cloud environment, identifying and remediating critical risks, adopting best practices, and shifting security left to prevent issues before they reach production. This approach embeds security into every aspect of cloud operations, creating resilient systems that can withstand modern threats while maintaining the agility and scalability benefits of cloud-native architectures. The cybersecurity risk management process is a structured, four-step approach that forms the backbone of effective security strategies in SASE environments. This methodical framework enables organizations to address cyber threats while maintaining operational efficiency in a systematic manner. The four steps include risk identification, risk assessment, risk mitigation, and risk monitoring and review. The first critical step involves recognizing and cataloging potential vulnerabilities across your digital ecosystem. This process begins with a comprehensive inventory of information assets, including hardware, software, services, networks, and human resources that cyber criminals could target. A thorough risk identification phase requires conducting vulnerability assessments to expose weaknesses in systems and applications, classifying assets based on their importance and sensitivity to the organization, considering both internal factors, such as configuration issues and external threats, and documenting all potential attack vectors that could compromise security. This foundational step creates visibility into the organization's risk landscape, establishing a baseline for subsequent analysis and mitigation efforts. Once risks are identified, they must be evaluated to determine their potential impact and likelihood of occurrence. This analytical phase involves estimating the financial, operational, and reputational consequences of each identified risk, determining the probability of threats exploiting specific vulnerabilities, prioritizing risks based on their significance to the organization's operations, and conducting impact analyses to quantify potential costs and business disruptions. Risk assessment transforms abstract threats into measurable business concerns allowing security teams to focus resources where they'll have the most significant protective effect. This step often leverages frameworks like NIST SP 830, which provides structured guidance for federal information systems, but serves as a valuable model for private organizations as well. After prioritizing risks, organizations must implement appropriate controls and strategies to address them. The mitigation phase includes developing tailored strategies to reduce identified risks based on their severity and business impact, implementing technical controls, policies, and procedures to minimize vulnerabilities, and selecting appropriate risk treatments, which may include risk acceptance, avoidance, transfer, or reduction. It's also important to enforce cybersecurity policies that align with the organization's risk appetite and business objectives. Effective mitigation doesn't necessarily mean eliminating all risks. Instead, it involves making informed decisions about which risks to address based on a cost-benefit analysis and organizational priorities. For many organizations, purchasing quality cyber insurance has become a crucial component of their risk management strategy, offering financial protection against residual risks. The final step acknowledges that cybersecurity risk management is not a one-time effort, but a continuous process that requires vigilance and adaptation. This ongoing phase involves continuously monitoring the effectiveness of implemented controls and security measures, adapting strategies to address evolving threats and changing business environments, conducting regular tabletop exercises that include executives, board members, IT departments, and PR teams, and reviewing and updating the risk management plan based on new vulnerabilities, threats, or organizational changes. Regular testing is crucial to validate what works in the plan and what needs improvement. Organizations should gather feedback from each department after testing exercises and incorporate those updates into their cybersecurity protocols. The cyclical nature of this four-step process ensures that security measures remain effective despite the constantly shifting threat landscape. By continuously identifying, assessing, mitigating, and monitoring risks, organizations can maintain a robust security posture that protects critical assets while supporting business objectives. Microsegmentation implementation requires a methodical approach that balances security needs with operational realities. Unlike traditional network segmentation, which focuses on broad perimeter defenses, microsegmentation creates granular security boundaries around individual workloads, applications, and services. This strategic approach complements Zscaler's Zero Trust Exchange architecture by extending zero trust principles to internal network communications. Successful microsegmentation deployments follow a graduated implementation strategy rather than attempting a big bang approach. Organizations should adopt a phased methodology that includes, first, starting with broad segmentation by establishing environmental boundaries between development, testing, and production environments before progressing to more granular controls. Second, gradually refining policies from application-level segmentation or ring fencing to tier-level segmentation such as web, application, and database. And finally, to process-level microsegmentation for critical assets. Third, prioritizing high-value assets by identifying and protecting the most critical systems, applications, and data first, focusing security efforts where they matter most. This incremental approach prevents overwhelming security teams and allows for proper testing and validation at each stage of implementation. Before implementing microsegmentation policies, organizations must gain comprehensive visibility into their network architecture and traffic patterns. Asset discovery and mapping are essential to create an accurate inventory of all network components, applications, and their interdependencies. Traffic behavior observation helps identify legitimate communication patterns that must be preserved while blocking unnecessary pathways that attackers could exploit. Vulnerability data integration enhances segmentation strategies by highlighting which segments contain vulnerable systems requiring additional protection. As one Reddit user noted, the whole concept of microsegmentation involves isolating workloads into smaller independent segments. This isolation requires detailed knowledge of how these segments normally communicate. The core of microsegmentation lies in creating and enforcing granular security policies. Defined policies based on multiple criteria, including user roles, device types, application requirements, and security levels to create context-aware access controls. Involve key stakeholders from IT, security, compliance, and business units to ensure policies align with organizational objectives while maintaining security. Apply vulnerability-based microsegmentation as a compensating control to mitigate exposure to known vulnerabilities that cannot be patched immediately. Effective policies should be both granular enough to provide meaningful security and scalable enough to accommodate network growth and evolution. Implementing microsegmentation demands appropriate resources and expertise. Assemble a dedicated project team, typically consisting of an executive sponsor, security architect, technical lead, and project manager, with vendor support when needed. Provide comprehensive training to ensure all team members understand microsegmentation concepts and implementation strategies. Recognize departmental responsibilities with the understanding that application owners may not fully comprehend microsegmentation, placing greater responsibility on networking and security staff. An executive champion is often crucial for securing necessary resources and budget, as microsegmentation initiatives frequently require significant investment in both technology and personnel. Microsegmentation should not operate in isolation, but rather integrate with existing security infrastructure. Connect with log and event management tools to monitor network traffic and detect potential policy violations or security incidents. Incorporate threat intelligence to adapt segmentation policies based on emerging threats and attack patterns. Leverage multiple deployment approaches, as most environments are not homogeneous, requiring different microsegmentation technologies for various network areas. This integration creates a comprehensive security ecosystem that enhances visibility while providing multiple layers of defense against sophisticated attacks. By following these implementation strategies, organizations can effectively deploy microsegmentation to reduce their attack surface, prevent lateral movement, and align with zero trust principles, creating a more resilient security posture that complements cloud-based security platforms like Zscaler. Identity-based access control, or IBAC, represents a fundamental security model that governs access to resources based on the verified identity of individual users or entities. Unlike traditional perimeter-based security approaches, IBAC places the user's identity at the center of access decisions, ensuring that each individual receives precisely the appropriate level of access to systems and data. IBAC operates on several key principles that differentiate it from other security frameworks. First, identity centricity. The model focuses primarily on who the user is rather than where they are connecting from, making it particularly valuable in distributed environments where traditional network boundaries have dissolved. Next, granular authorization access permissions are explicitly tailored to individual identities, allowing for precise control over who can access what resources under which circumstances. Then, dynamic policy enforcement rather than static permissions. IBAC enables context-aware access decisions that can adapt based on changing user attributes, roles, or environmental factors. And finally, attribute-based decisions. Access control policies in IBAC are defined based on attributes associated with users, resources, and the environment, enabling fine-grained control that goes beyond simple role assignments. A comprehensive IBAC system typically consists of several interconnected components. These include identity verification mechanisms, which ensure users are authenticated as who they claim to be, using methods ranging from passwords to biometrics and multi-factor authentication. Access permission frameworks are also essential. These systems associate specific permissions with verified identities, determining which resources each user can access. Centralized identity management is another key piece, providing a unified system that maintains consistent user identities and attributes across the organization, which really helps with coherent access control enforcement and, of course, policy definition and enforcement. These are the rules that determine how identity attributes translate to access decisions, along with the technical means to enforce these policies at access points. In contemporary security frameworks such as Zero Trust, IBAC serves as a foundational element. Rather than assuming trust based on network location, these architectures verify identity for each access request before granting permissions. This approach aligns perfectly with distributed work environments where users access resources from various places and devices. The implementation of IBAC provides several significant advantages. First, reduced attack surface. By limiting access based on verified identity rather than network location, organizations can minimize potential entry points for attackers. Next, improved compliance capabilities. IBAC facilitates detailed tracking of who accessed what resources and when, supporting regulatory requirements for access monitoring and auditing. Enhanced security granularity is another benefit, as organizations can implement precise security controls that match business requirements without resorting to overly permissive access policies. And finally, adaptive security posture. As user roles and responsibilities change, access permissions can be dynamically adjusted without requiring reconfiguration of the network infrastructure. IBAC represents an evolution from earlier security models that relied on perimeter defenses or broad role-based permissions. Its focus on individual identity verification and contextual access decisions makes it particularly well-suited for securing modern digital environments where traditional boundaries have become increasingly blurred. When implemented as part of a comprehensive security strategy, IBAC helps organizations maintain the delicate balance between security and accessibility, ensuring that legitimate users can access the resources they need. In contrast, unauthorized access attempts are effectively blocked.